First, I want to pause a few seconds to pay our respects to the people in Ukraine who are fighting for their freedom and for our freedom. Okay. Today, I want to first start by finishing what we started last week, talk about the long tail, and then I'll finish talking about cascades. This is very interesting that you all know how to manipulate the network for fun and profit. Okay, so last week we talked about web popularity. I'm not going to go through everything again. We saw that a web page popularity is a power law. It's like 1 over k squared. K is the number of inlinks. And that means that it's even, there's going to be a very, very large number of pages because it only goes down very slowly when k increases. Okay? And that was determined experimentally. And here's a model. This one is called Preferential Attachment. And this explains the power law. And it's not like many independent decisions, which is what natural law physics experiments have. Huh? If you make experiments, you will get an error, and it's distributed like normal distribution. This is totally different. And preferential attachment means it's a model for how the web is built. And when you create a web page, you make a link to an earlier page. Okay. Please, I would not like people to discuss while I'm giving my course. So when you create a page, I'm sorry, do you have something to say? No, I want to please teach my course. Thank you. When you create a page, you make a link to an earlier page, and either it's a random page, but actually you also can repeat previous decisions. So instead of pointing to a random page, you pick the random page and you use the link that's on that page. So you repeat the previous link. And this gives you a power law. Okay? And rich gets richer, which means that popular pages will get even more popular. Okay? Some people call this the Matthew principle, because there's a Bible story in the Gospel of Matthew where it says the rich will get richer and the poor will get poorer. If you know your Bible studies. We are in a Catholic university. Anyway. Okay, so let me now explain the consequence of this, which is called the long tail. In French, it's the long traîne. The long tail. So the power laws actually have huge consequence in economics. So if you're a company selling things, books or music, what's making your profit? Small number of very popular things, or a large number of obscure things? So do you have hits? Do you have Harry Potter? Or do you have a large number of niche products? Actually, it turns out that in the web, in the internet, it's all pointing to the niche products. Most of the profit of Amazon does not come from the hits, but it comes from the huge inventory they have. And this was called the long tail. So this was first recognized in 2004 in an article called The Long Tail by Chris Anderson. So it's called the long tail. A long tail of obscure products is what makes it work. And this is why Amazon and Netflix are very successful. Because a physical store made of bricks cannot have a million different things. But Amazon has millions of different things because it only has to exist on the internet. And so that's why Amazon has a major advantage over any physical store. They have a huge inventory, which is much easier on the web than in a brick and mortar store. Okay? This is already known, in fact. Supermarkets have the same advantage. A big supermarket has thousands of products, 10,000 maybe, and this is a major attraction, even though most of the products are not selling very much. But if the supermarket would only sell a small number of hits of most popular things, then they would not be successful. It's weird, huh? It's the obscure things that almost nobody buys that make it successful. Okay? So we can see this from the power law. Okay? Here's a graph for a bookstore. The sales volume of how many books. Okay? So which book? So this is actually the name of the book, huh? So you have a huge sales volume, but only a small number of popular books. Harry Potter books, for example, they have a lot of sales volume. But you have also books with almost no sales volume. So this graph actually focuses on the popular books. You see, this with a huge sales volume. But let's flip the graph and focus on the others, the unpopular books. Here are the books. The books numbered 1, 2, 3, all the different books. And here is the sales volume going down, down, down. So you have a huge number of books with very small sales volume. This part of the graph is called the long tail. La longue traîne in French. And this goes down very slowly because it's a power law. It's not exponential. Exponential would go down very fast to 0. But power law, 1 over k squared, for example, goes down very slowly when k increases. Okay, so this is a very long, long, long part of the graph, and the total volume of sale here is a lot. Okay, so the total sales of all the unpopular books is larger than the popular books which are here. So all the obscure books that people buy, like textbooks or random novels about weird things, there's thousands and thousands, millions of them. Altogether, they have a lot of sales, even though one book maybe only sells 10 copies per year. It's not very much. But if you have millions of them, then it sells more together than all the Harry Potter books. And this is the advantage of Amazon. Okay? If you want to make a web commerce, then this is what you are taking advantage of. This is why Amazon is successful, because of the long tail. And this was a bet by Jeff Bezos, by the creator of Amazon, which took a long time to make profit. He was not sure it was going to work. But because of this property, it works very well. And this is the big advantage of web commerce, and why, for example, it's very bad for physical bookstores. But now the physical bookstores are also selling their stuff on Amazon, so they're joining into this technique. Okay? So that's the long tail, and it exists because of the power law of popularity. Books popularity. Okay? And an important piece of advice if you want to create an internet company. Okay? So that's what we saw last week. So the power law, the rich get richer, and the long tail. Okay, so now I can start what I want to talk about today. Today I want to finish talking about cascades, how information propagates on the net, on the social networks, how things propagate. Okay, so I'm also going to kind of give a summary of the whole course to help you put the whole course into your brain. Remember, the course is organized as 5 parts. The first 2 parts is graph theory and game theory, which we then used. And the last 3 parts, most of it is markets, and this is actually applying game theory and also networks and graph theory, like when we had intermediaries or bargaining, and also the diffusion, the informational cascade or direct network cascade, how networks influence people's behavior. And today we're going to finish this by showing how things diffuse on the network. And we also talked about the World Wide Web. And we made many formal models. So this you know by now very well. So the whole course is a huge collection of idealized formal models that give intuition. And today we're going to finish the discussion of cascades. In the last 2 weeks, we saw 2 kinds of cascade. One is what's called information cascade, when people make decisions in some order, and we use Bayes' rule for that. And the second one is called direct benefit cascades, when you have benefits when there's lots of people using it. And we used an economic model, a continuous economic model for that. And we showed the equilibria, even the tipping points, okay? And today, we're going to show how the actual structure of the network, like your friends, your neighbors on the network, depends on who you know, so the information kind of propagates. In the first 2, we assumed everybody kind of sees everybody. We didn't really assume anything about the network. But now we're going to assume that you only have a small number of neighbors. Okay? So that's what we're going to talk about today. How the network structure influences cascades. Okay? So in the previous lectures that we saw the network as homogeneous, that a whole bunch of people and everybody sees everybody else. But today we're going to look at the actual connection. Everybody has only a small set of neighbors. It's a graph. And the cascade actually goes through that graph. It's not as simple as what we saw before. If you assume that you have neighbors, it's going to be like diffusing. Okay? You make decisions depending on your friends, your colleagues, your neighbors, and it's not so simple, the direct benefit or information. Sometimes you only look at what your friends are using. Okay? So remember when we had homophily, that you're similar to your friends. Well, this is related to that. Here, the similarity is also going to affect, the graph is going to affect the diffusion. Okay? So let me first give you some intuition, some examples of how it works. And when new things come, they kind of propagate in the network, like innovations, electric cars or gasoline cars or whatever, telephones. And it's interesting to see, whenever you have an innovation, it has 2 waves. The first is when people learn about it, and the second, but they don't use it, the second is when they actually start using it. So the first one comes, when people learn about new medicine or new things, electric cars, but nobody buys it yet, and in the second wave, people start using it. Okay? So the first wave is information that is propagating. And here's 2 examples. The adoption of a new kind of corn among farmers in Iowa, hybrid seed corn. Okay, so farmers are usually very conservative because they don't want to take a risk about their crops. But they learned about this new crop from salesmen. That's the first wave. But they didn't use it yet. But later on, when when a farmer sees his neighbor using it, says, ah, the guy, it works very well for him. I will use it too. So the second wave comes from the neighbor's experience. Another example is new medication, new drugs, like tetracycline. Okay, so this, first doctors learn about it because they read publications. Okay, this new drug. But they don't use it yet, they're not sure. But then the doctor, they go to some medical meeting and they see some friends who are doctors and they say, it works very well. And then they, because of the social connection, they start using it. So there's always two waves, okay? So the new thing means that there's a risk, but ultimately it's a good thing. So you have early adopters, and then it kind of propagates from that, okay? So you can see people that travel a lot, or people that have higher socioeconomic status, they maybe will be early adopters. They learn about it quicker than the others, and then it propagates to everybody else. Okay? So the first wave is information. The second wave is when people actually use it because of the benefits. The neighbor is making a benefit, I use it, like Temple's examples that this we saw before, telephone, email. Email is only useful if everybody has an email, and the same for the phone. And there's some principles on this. So the new thing has to have an advantage. It has to be simple, not complicated like smartphones. Strange how people are spending so much time, but normally it should be simple. It should be observable. People can see other people using it. It should be trialable. It means you can try it out without taking so many risks. And compatible with the social system. You don't have to make a revolution to start using it. Okay? Now, if you have an area where a lot of people know each other, like a tight community, a small village where everybody knows, then the innovations will come from outside, and there's some kind of a barrier. It's harder when you have this tightly knit community. And that's something we're going to study today. Okay? And I will explain now a model for how things will propagate on network in two parts. First, I'll talk about cascades, which is how neighbors tell neighbors. And in the second part, I'll talk about how the propagation is blocked. So that's using something called a cluster, which is like tightly grouped people who don't want new things, okay? And so the first part is the cascades, how things propagate, okay? So a person has neighbors, and they see what the neighbors do, and they will decide what to do depending on the neighbors. Okay, so we're going to attach our model to this a direct benefit thing. So the user will decide to do it if that user gets a benefit because of the neighbors. That means if all the neighbors are doing it, then the user will have a benefit. Okay, because everybody is using it, and they will decide to use it. Okay? So the more and more neighbors using it, the more you will chance that you will use it. Okay? And we're going to study this first by a small idea from game theory. As soon as there's like a good payoff, then you do it. If enough neighbors are doing it, then you will do it. Okay? So the model starts with a little bit of game theory. So you have two people, V and W. They know each other, so there's an edge. And each has a choice between A and B. iPhone or Android phone, or Samsung phone, for example. And if they both have the same, then there's some advantage. If they're both using iPhone, then they can exchange apps and have some advantage, and the same for Android. So we have this payoff matrix here. If the two individuals both pick A, they get an advantage. A, little a, little a. If they pick B, they get an advantage, little b, little b. But if they pick different thing, they get no special advantage. Okay? So this is a simple coordination game, and this encourages somehow these two individuals for doing the same thing. Okay? But that's only one edge. In a real graph, okay, there's many edges. So here is somebody, V. V has neighbors. So assume V has D neighbors. And some fraction are using A, and some fraction are using B. Now the thing is, what is V going to do? Is V going to use A or B? So it depends on whether there's an advantage. We're going to assume the payoff for V is the sum of the payoffs. So if V chooses A, the payoff will be on this side. Okay? It's P times D, which is the number of edges here, times little a. So it's PDA. If V chooses B, then there's number of neighbors is 1 minus P times D. So the payoff is 1 minus P times dB. And now we compare these two. When is this payoff greater than this one, or equal? Well, A is a better choice if P is greater than or equal to B over A plus B. So you can calculate this number by starting to compare these two. Okay, so I won't do that, but you do that. So there's a threshold. So we'll call it Q. So there's a threshold depending on how these two advantages are related. So A has the advantage little a, and B has the advantage little b. And so the threshold for choosing A is that it's bigger than B over A plus B. Okay? And with this, we can start now doing propagation in a graph. Okay? So this is the basic idea coming from game theory. Okay? Now, what does it kind of mean? So if you look at a network with many friends, many nodes, there's actually equilibria on this network. Maybe everybody has A, okay, that's fine, then everybody has an advantage. Or everybody has B. Those are two equilibria. And we can maybe tip the network from one to another. Everyone starts by using Android. At the end, they all flip to using iPhone or vice versa. But there's actually an interesting question. Is there some in the middle cases? Is it possible that part of the network is using A and part is using B? There's a part using iPhone and part using Android phones, and they don't. And it's stable. It's not flipping. And we will have this very interesting question. Sometimes the diffusion kind of stops. Okay? So let's try some examples now. We'll say all nodes are starting with B. We have a small set of initial adopters, a small set of nodes using A, and then we say, do the others flip? So all the other nodes will evaluate the payoffs, and some of them might decide to switch to A, and that will make other ones switch, and so on. It's like a cascade. Okay? So let me show you an example of that. Here's an example. Here we have a network with a bunch of nodes. And each node has some friends, U, W, R, S, T, U. And assume that the little a is 3 and little b is 2. So the payoff for A is 3 and the payoff for B is 2. So A has a little bit of an advantage over B. Okay? And the threshold is B over A plus B, so it's 2/5, 0.4. Which means you flip if more than 40% of your neighbors are using A. Then you flip. You see, it's less than half because A is a little bit better than B. Assume now that in here, V and W are the initial adopters. So what happens to the other nodes? Well, look at node T. Okay, T has 3 neighbors, and 2 of them are doing A. That makes 2/3. Okay, and the same for R. 2/3 of the neighbors use A. 2/3 is bigger than 2/5. So that means that R and T are going to flip. They're going to use A because it's a higher payoff. And now it's kind of like chain reaction. S and U, what do they do? So if you look at S has 3 neighbors, but 2 of them are using A and 1 of them is using B. So S will also flip, but U will flip. So they all flip. So in this case, the whole network flipped from B to A because of how it's structured, but also because of the thresholds. Okay? That's one example, but it's not always going to be like that. Okay? Where they all flip. Here's another network, more complicated one. Okay, so again, assume that little a is 3, little b is 2, so the threshold is 2/5. So you need to be higher than that to flip. Assume 7 and 8 are initial adopters. So they go to A. They start using A. What happens now? Well, if you look at node 5, 5 has 3 neighbors, and 2 of them are using A. So 5 is going to flip. Okay? If you look at node 10, that's interesting. 10 has 4 neighbors, and 2 of them are using A. That means 50%. But the threshold is 2/5. It's 40%. So 10 is going to flip. Okay? And also node 4 will, after 5 flips, node 4 will flip. Node 9 will flip because it has 4 neighbors and 2 of them are going to be A's. So 9 is going to flip. And 6 will flip because 4 and 9 are A's. And then it stops. Okay? And then nothing happens anymore. So this is kind of interesting. Now, somehow it doesn't go any farther. For example, here node 11 has 3 neighbors. 1 of them is A, but that's 1/3, which is less than 2/5, 33%, 40%. And the same for all of these. They're not going to flip. 2 is not going to flip either. Okay, so this is a cascade, and it stops here. Okay, it has a stability here, equilibrium. It doesn't go farther. Okay. Now, so you see, there's 2 possibilities, huh? In this possibility, all of the nodes flipped. In this example, but in this example, some of them flip, but not all of them. So that's the difference. So what does it mean, this difference? How do we know when it's going to stop? Okay, so we're going to study that. How do we know when the flipping stops? Okay, so let me introduce a definition. So there's 2 possibilities. The cascade runs for a while, but it stops without flipping all the nodes. And the second possibility is it flips everybody, and that we call complete cascade. And I want to introduce that as a term. Huh? So if you have initial adopters with behavior A, and all remaining nodes have B, nodes repeatedly evaluate the decision whether to switch using a threshold of Q. If the result eventually causes all nodes to switch, the whole graph, we say that the set of initial adopters causes a complete cascade at threshold Q. The whole graph has flipped. Okay? Now, that doesn't always happen. So when does it not happen? That's very interesting to see. And we're going to study that. It does not happen. That's where we introduce this notion of a cluster. It's like a barrier that blocks things. Okay? So we're going to study when does it happen, when does it not happen. But before introducing the formal model of clusters, let's get some intuition on this. Okay? some general observations. So the first observation is a tightly knit, a tight community can hinder, can stop the spread. If you look at the example here, this community is kind of tightly coupled, and there's just a few links here, and the propagation is stopped. So a tightly knit community is going to stop it, okay? And it's like in the real world. You can have a community of people with one political idea and another community with another one, and the ideas don't propagate, or between Mac users and PCs or whatever, okay? So you have this coexistence of different decisions. Okay, so that's one thing. Second thing, if you want to force the flipping, what do? Well, you can change the threshold. If the maker of A improves the advantage from 3 to 4, okay, then the threshold will drop down to 1/3. That means more people will have incentive to flip. And in the previous example, if you do that, all nodes will switch, so you can check it out. Or another way is you have some people, influencers, you convince them somehow to switch, like nodes 12 and 13. So if you look at this, if I can convince some nodes to switch, like these nodes, then all the others will switch. Okay, that's one way. Okay, convincers. Okay, but if you try to convince 11 or 14, won't do anything. You have to pick the right people. So you can see this is actually very different from direct benefit. Okay, if you are purely working in big scale, direct benefit, like what we saw the last time, remember there's this tipping point and you have to get over it. That's very hard. But in this example, now, if you know the network, it's actually easier because you just have to change a few people in the right places. You only need to worry about the neighbors. A few influencers. So if you know about the network, it can actually be easier. Okay, so that's some intuition. Okay, now let me show you the second part of the model. So the second part is the clusters. So that's the thing that stops the diffusion. And when you understand that, then you can kind of think more about the whole picture. Okay. To explain it, here's another network. Okay. You have A, B, C, D kind of connected closely. And D and E is like a bridge. And then you have E, F, G, H, and then H and I is like a little bridge, and you have 4 more, I, J, K, L. So a diffusion can stop when it tries to break into a tightly knit, dense community. So that's kind of the intuition. But we want to make it precise now. We want to understand. What does it mean? A densely connected community. What does it mean? Well, I mean, mathematicians and graph theoreticians, they thought about that. They tried some examples. Eventually, they came up with this definition, which seems to be the right one. So we're going to define a cluster of density P. It's a set of nodes such that each node has at least a fraction P of its neighbors in the set. So that's kind of a funny definition. If I have some nodes, for example, here, a cluster. So this one has 1, 2, 3, 4. So this node, A, has 3 neighbors in the set and 2 neighbors outside. Okay? So the fraction of neighbors in the set is 3 over 5. Okay, and we can maybe do similar things for the other ones. Okay, for this node it's 100%. For this node it's 75%, and so on. So this would be a cluster of density 3/5, 0.6. Because this node has 3 out of 5 neighbors in there. This node, B, has also 3 out of 5. This node C has 3 out of 4. So that's at least, that's good, at least 60%. This node has 100%. That means for the nodes A, B, C, D, this is a cluster of density P. And we cannot increase this because A and B is exactly 60%. You see? So we're worrying about the neighbors that are in there and the neighbors that are out. So a cluster kind of groups nodes according to their neighbors. Okay? This is the definition we're going to use, this cluster thing. So a high density cluster is going to be more tight than a low density cluster. Okay? Okay, so let's think a little bit about cluster. So each node in a cluster has some fraction of its friends in the cluster. So it's like together, cohesion. But that's still kind of, it's not that cohesive, in fact. The whole network, all nodes, is always a cluster of density 1. Okay, if you look at the whole network, then all the neighbors of a node are in the network, so it's density 1. Okay? If I take 2 clusters of density P, and I make the union of them, it's also a cluster of density P. If I have a cluster here, and another one here, with nodes, and they both have density P, if I take the union of them, it's also a cluster of density P. But there's no connection between the two, okay? Still, it's a cluster of density P. You can prove that if you look at the definition. P, fraction P of the neighbors are in the cluster. That's still true for every node when you do the union. So you can prove this. That's a good exercise to understand what clusters mean. Also, you can have big and small clusters, many scales. You can have very small, but also huge clusters. So cluster is kind of a curious concept, but it seems to be the right one. It's the right concept for cascade. Okay, so let's look again at our example. Look at this example. Remember the one we just did? 7 and 8 are the initial adopters. There are 2 clusters of density 2/3. This one, why is it 2/3? Well, because node 2 has 1 neighbor outside, so 2/3 of the neighbors are inside. Here, for example, node 11 has 1 neighbor outside, 2 are inside. 1 are outside, 2 are inside. 1 is outside, and 4 are inside. So again, it's a cluster of density 2/3. Okay? So it's somehow tight, density 2/3. Now notice, it's very curious, 2/3 is bigger than 2/5. 2/5 was the threshold for the discrimination. And these 2 clusters are exactly the 2 pieces that did not flip in the example. So is this a coincidence? Is this a general principle that the density of the cluster here is somehow related to the threshold? Okay? Yes, it is a principle, in fact, so we can prove it. A cluster can stop a cascade depending on the density. Okay? We're going to show a cluster, if you have a cluster in the network, with a given density and you have a cascade with another threshold, then the cluster can stop the cascade if the density is big enough. Okay? We can actually make a theorem, okay, on this. Okay? Consider a set of adapters with threshold Q, then in the network, okay, to adopt behavior A. We can show this. If the remaining network, so the ones that are still media, has a cluster of density greater than 1 minus Q, then the adapters will not cause a complete cascade. Okay? And we can also prove the opposite, so it's if and only if. If the adapters does not cause a complete cascade, then there exists a cluster with density greater than 1 minus Q. So it's basically if and only if. A complete cascade is blocked if the remaining network has a cluster of density greater than 1 minus Q. So the density and the threshold are what are fighting each other. Okay? Right? If the cluster is dense enough, then you won't be able to go in there. Okay? So we can prove, let me prove it. We can prove it. I'll prove each of these separately. So the first proof is that there is a cluster. And I will show if there is a cluster, then the cascade will stop. Okay? There is a cluster of density greater than 1 minus Q. This is the first part. So here's a cluster. Okay? This is a cluster of density greater than 1 minus Q. Here's a node V. We can show that V will not adopt A because of it's in the cluster. Okay? So we can prove that. We prove it. Let's assume the opposite. Let's assume V has adopted A. Okay? The earliest time step. That means all the neighbors of V using A were outside of the cluster. Okay? But the cluster has density greater than 1 minus Q. That means less than Q of the neighbors are outside. But it has to be bigger than Q for the adoption, not the switch. But because it's all in, it's less than Q outside, so it won't switch. That means V will not switch because of the cluster. Okay? See, that's the first direction. We can also prove the opposite direction. Assume that the diffusion stops. We'll prove that there's actually a cluster in there. Okay? So there's not a complete cascade. That means assume it stops. Then we can actually prove that the remaining network must contain a cluster of density greater than 1 minus Q. And we can prove that too. Okay? So here, assume the set of initial adapters, it fails to cause the cascade. The cascading stops. Okay? So here's the diagram. So here's the initial adapters, and they switch, and they switch, and they switch, and it stops here. We have to show there's a cluster. Okay? So let's S be the set of nodes that do not switch. Okay? W is part of S, so they're all on the top here. W does not want to switch. So the fraction of neighbors using A of W is less than Q because it doesn't switch. Okay? So the fraction using B is the opposite of that. So it's greater than 1 minus Q. Well, that's exactly the definition of a cluster. Okay? It has a fraction of nodes, not using B, that is greater than 1 minus q. That means all the nodes in S together, they form a cluster. So a cluster is actually exactly the opposite of a cascade. Huh? Okay? So with this, you can actually study how the network will travel. Okay? The network, how the diffusion will go on and on and on. And at some point, it stops. And it stops because of the cluster. So that's our formal model. And with this model, we can now have some intuitions. Huh? We're going to look at some intuitions coming from this. So the cascades will keep going until they hit clusters, which block them. And then they stop. Okay? So you can, if you know the network, and you know the value of the threshold, and you know the density, you can actually figure out how it's going to evolve. You can also know how to fix it. If you're a company, you want to get rid of a cluster, well, you have to somehow find out how to get rid of it. Either you increase the threshold or you somehow reduce the density of the cluster. Now, there's different approaches. Okay, so that gives us the first model. This tells us how information flows from node to node, okay? How it cascades and how the clusters block it. Okay. Now, let me make a break, and then we will look at some variation, and we try to increase the intuition. And I'll also explain to you, if you want to start a revolution, I'll tell you how to do collective action, which is, if you want to start a revolution, I'll explain exactly how you're supposed to do it, according to our mathematical model. Okay. So let me make a small break. Continue now. Now I'm going to show you some smaller things. So the big thing was the model of diffusion with cascades and cluster, and this is a very general kind of model. Now I want to show you some kind of things on the edge that help you kind of understand different effects and how things work in society and on the networks. And the first thing I want to talk about is weak ties. So a weak tie, remember a long time ago when we saw graph theory, we had strong connections and weak connections. The strong connections were like friends, and the weak ones were like acquaintances. Remember we had the Grunweder thing where if you find a new job, the information comes from an acquaintance and not from a close friend, because it comes through a bridge, and the bridge will be a weak tie. Okay? So the weak ties also play a role. And now I want to say a little bit about the weak ties. And this is related to this idea of the first wave and the second wave. And here's an example. This is the hybrid seed corn thing. The farmers using the new kind of corn that's more productive. And this is the year, 1924 up to 1941. So this was a long time ago. And there's a small percentage of farmers who never accepted it. You see that the white bars here are the first wave, when they learned about the new idea. So they learn about it, some percentage are learning every year. And here, 2931, the most learned. But they're not using it. You say, oh yeah, this is nice, okay, but they don't use it. And then later, they actually start using it. So a few are using it here, but a very small percentage. And then it goes up, and here, a lot are going to start using it, and then they get good experience, and they start using it. So you see there's a big difference. 30, 31, and this is like 37, it's like 7 years difference between those two, okay? And the same happens with our cascade model. Huh? If a node does not flip, okay, because it's not above the threshold, it still learns about the other one, which we didn't really talk about. It still learns about it. So the first wave will still go on, even if the node does not flip. Flipping means adopting the thing, using it. And in our cascade model, the flipping means adopting. But we didn't really explain the awareness, the learning about it, because that is never really blocked. Okay, that one will always diffuse. Whereas the adoption, it might get blocked, but then there's one farmer who's like very influential, okay, and he's not using the new thing. But then, whatever, he retires, his son takes over, or he changes his mind or something, and then the cascade goes on. So the adoption is delayed compared to the information, okay? So we didn't really talk about the information cascade, but it's also there, and it's a little bit before the other one, huh? And this is the weak ties. So there's more weak ties than strong ties, huh? So awareness is easy. And this, remember we saw this a long time ago, huh? Remember the local bridges? Here's a local bridge, here's another local bridge. They provide access to information. Remember that? The acquaintance gives you the information for finding a new job, and not the friend. So new information comes along these links. But these links will not cause flipping. Okay, they're weak links, and it doesn't go beyond the threshold. So they're not going to flip. Okay? So if W and X are initial adopters, U and V will not flip. They will not adopt. They will learn things. So the bridges, and the local bridges that we saw before, they transport awareness. So the first wave, but they don't transport the second wave, which is what our model shows. Weak ties, they only convey awareness. If you want adoption, you need strong ties and you need to be over the threshold. Okay, and that can change over time, of course, if nodes change their opinion or if the network topology changes. So there's a lot of techniques for getting rid of clusters or for improving the threshold or whatever. But the weak ties is only for the first wave. Okay? And one of the things that I'm going to talk about today in the rest of the course is social movements, society. Social movements, so changes in society happen slowly, okay? They happen slowly, they build support slowly, even though the awareness is fast. For example, if you look at the Bolshevik Revolution of 1917 in Russia, the whole world learned about this very fast, okay? The world-spanning network of weak ties will spread awareness very quickly, okay? That's the first wave. But actually changing the behavior, changing the political organization, for example, is much, much slower, because there everyone is deciding whether to flip or not, okay? And usually they will only really flip if the advantages are big, if there's lots of neighbors with big advantages. And we saw that, and if you have a cluster, you can block it. Of course, the social movement will try to break the cluster somehow. These clusters will slow things down a lot. So any kind of social movement is very risky. So who knows? Things might get worse if things change. So the threshold is very high. Local bridges will not be useful. Okay. So the weak ties, awareness, they can be very wide, geographically, very spread out. But the strong ties will be very close by, because it will be people you know very well, people close. So they spread geographically, Okay? And if you want to convince people to keep growing the movement, you need strong ties also. Okay? So the difference, the strong, the weak, and the strong ties. You see the point here, the diffusion, what we saw, is depending on strong ties, people really making decisions, whereas the information passes very quickly and depends only on weak ties. Okay? But the information doesn't change very much. If you want to change things, then you need strong ties. Okay? So that's a kind of a comment on this model. Now let me make another kind of variation, what I call heterogeneous thresholds. And the point is that people might have different thresholds. And the idea is we take our basic model here, we can make like variations on it, and it keeps the intuition. So one of the variations is that each node, the A and the B is a different number. Some nodes are very easy to convince. Some nodes are very hard to convince. Okay? So each node will value them differently. And it turns out, if you do that, each node has a separate threshold, then all what we saw before is still valid. Okay? The theorem and everything is still valid. So for example, the cascades will be different. You might have influenceable people who are easy to change their minds. These are people with low thresholds. Okay? They will favor the cascades, but you still will have clusters, and they will still block cascades. Only the definition, the composition of the cluster is a little bit different. Okay? So it looks like this. So again, if I have two people, V and W, but V has payoff AV and BV for A and B, and W has AW and BW. So this gives you a new game, but the only difference is that the payoff is not two numbers that are the same. It's AV, AW, BV, BW. And if you calculate the threshold for n nodes, the V node in the middle, you can see that each node will have its own threshold. Instead of having one threshold which is the same for all the nodes, you will have, every node has a separate threshold. And that means the node will flip if the P, the number of neighbors using A, is bigger than the node's threshold. So if the node has a low threshold, this will be easier, but as high threshold, it will be harder. Okay? So that doesn't change very much. So you can have influenceable people or not. Okay? And here's an example. So here we have a network with a bunch of nodes. You can see next to each node, I put the threshold. So node number 3 has a 0.1. Node number 4 has 0.7. And assume that node 1 is the initial adopter. Okay? Now who's going to flip? Well, 3 is going to make it work. You see that? Because 3 has a threshold of 0.1, and it has 1 out of 3 neighbors, which is A, which is 0.33. So 3 will flip. But the others will not flip. 5, 6, 4, and 2 will not flip. So 3 is a very influenceable person. You know such people exist, no? So you can extend the model for this kind of people. Okay? And you can also define clusters. So here you have the threshold for the cascade, but the cluster can also be a little bit modified for the heterogeneous case. So a blocking cluster is a set of nodes for which each node has more than 1 minus QV fraction of its friends in the set. So this is a cluster that will block any kind of a transition. So a blocking cluster, if you come with less than QV, you will not, so if more than, flip. So if there's more than 1 minus QV in the set, then the cluster will block the flipping, okay? And you can prove the theorem. A set of initial adopters will cause a complete cascade if and only if the remaining network does not have a blocking cluster. But here, it's every node has its own little threshold value. See? So it still works. In this case, you will propagate up to here, but here I have a blocking cluster. Okay, so here I have 75%. The threshold is 0.3, so the 1 minus QV is 0.7, but there's actually 75% here. And here I have 0.4, but the 1 minus Q is 0.6, but I have 66%, which is more. So this is going to be a blocking cluster. It's going to block the cascade. Okay? So that's an example of extending the model. Now let me explain something interesting called collective action. So this is a new model. This is our second model for today. This was the first model, another formal model, and I'm going to talk about collective action. This is something that we do in a society, in a group of people, or people on the internet, okay? And assume we are organizing a protest, and we are living under some kind of repressive regime, okay? And tomorrow there's going to be a public demonstration, and if a lot of people show up, thousands, 10,000, the government will be weakened because they cannot go against all those people. But if only a few show up, they will all be arrested. It's not so nice. So what do you do? What should you do? This is a problem of collective action. How do you decide for a group of people to perform some action or not? Collective action problem. An activity provides benefits only if enough people participate. Okay? And the problem, though, is that there is very little communication. You don't really know what the other people's decisions are in this repressive regime. Okay? So a collective action becomes difficult if the communication is limited. So that's reasonable. And the repressive government, that's what they are going to do. Okay? They will control the internet. To not name any names, we can say China, for example. I'm not naming any names, but I will mention China, which will limit the communication. Okay? So this is a problem. And there's a related concept on this called pluralistic ignorance. This is actually a very useful and very common thing. Pluralistic ignorance, it means that people don't really know how common certain opinions are. You think that everybody is thinking a certain way, but they're not. For example, a majority of the population, they want a revolution, but since they cannot talk to each other, they think they are a minority. They think that the majority is not thinking that way. So this is called pluralistic ignorance, because their knowledge is wrong about what the society is thinking is wrong. They think they're in the minority, but they're not. They're in the majority, okay? And a real example of that is a survey in the United States in the 70s a majority of white Americans were against racial segregation, against it, but they believed that in their region they were a minority. So they believed that for the whole United States, people were, okay, there was a majority, actually. Most people didn't want it, but they thought that everybody in their community wanted it, everywhere, which is kind of weird, huh? So there's some kind of a dissonance. This is called pluralistic ignorance, okay? And a repressive government, they want to increase that, okay, the pluralistic ignorance. Most people are against this government, but they believe that they are in a small minority, so they take no action. So an unpopular government can survive for a long time, even if there is a strong opposition, because of this. If there was some way of the people knowing that everyone was against it, that would topple the government. So the conclusion is that if you limit the communication, this is the first wave now we're talking about it, you are increasing pluralistic ignorance and you make collective action difficult. Okay, let's introduce now a formal model. Let's say you want to do collective action. You want a group of people to agree on doing some action. And it will only work if they all agree. If they don't, they will not do it. Okay? So let me introduce now a formal model for this. So here's a network of people. Okay? Now the model is the following. We have a social network. Everybody has their friends. And everybody has a personal threshold. Okay? A number, K. It's somehow how much risk that person wants to take. I will join in the action if I'm sure that at least K people, including me, will join. So W, for example, will join in the action if W is sure that there will be at least 4 people in the action. So that's the first thing. There's a personal threshold. And the second part of the model is the strong ties. Each person knows their neighbors' thresholds, and they know what the neighbors are, but that's all they know. Because those are the people they meet. They will not know, they will not trust any information they hear. They will only trust the people they really, really know. So they will know each neighbor's threshold and their neighbors. So for example, W knows that U and V have thresholds 2 and 3, and that U has neighbors V and W, and V has neighbors U and W. Okay, but it knows nothing else. So typically in a bigger network, something like this one, so U knows W and V, but U does not know X. Okay? U does not know anything about X. Okay. Now we want to reason. In collective action, people are very conservative. They will only do it if other people do it. I will only join if I'm sure that K people will join. Okay? So what's going to happen? Well, in these 3 networks, let's say these are 3 like social networks. The first 2, nothing will happen. But in the third one, we will have an uprising, a collective action, a revolution will happen in the third one, but not in the first 2. And the model can explain that. Okay? So let me show you how it works. You have to do reasoning again for this. Typically you have to do reasoning, huh? So let's say the first model. It's like a chain. W will certainly never join, because W will only join when there's 4, but W only has 2 neighbors, so there's only a maximum of 3. So W will never, W wants 4 people, but there's only 3. But because W will never join, okay, if you look at V V needs 3 people. But V knows that W will not join. Therefore, V will not join either, because V only knows about U and V and W, and V knows that W will not join. So V will not join, okay? And look at U. U will now learn that V and W will not join. So U will not join, so nobody joins. You see, it's like a chain reaction, chain of reasoning here, right? So nobody joins, and it's like W is like the weak point, but it means nobody joins. The second one is a little bit more complicated. So if you look at U, for example, so U knows V and W, and he knows that V and W have a threshold of 3. Okay? But V and W don't know each other's thresholds, and there's also X. And U does not know X's threshold. Okay? Now the question is it safe for U to join? Well, not really, because if X's threshold is high, then V would not join, and then U would not join. So because of that, because the nodes are very conservative, U will not join. And it's symmetric, so nobody joins. Okay? The nodes decide not to join because the information does not propagate. Okay? So that's another case of not having a revolution. But the third case is an interesting one. Because the third case is where there will be revolution. And if you look at the nodes U, V, and W, they all have threshold 3. And each one of them knows the other two and knows the threshold of the other two. Okay? So they know U knows V, W, and W knows V, and U knows that W knows V. So this triangle is like a solid piece of knowledge, of common knowledge. Okay? So this is called common knowledge, where every node knows everything about the other one and vice versa. Okay? So X doesn't even really matter about X. So U and V, and so U knows that V and W can join, and therefore U can join, and V knows the same for the others, so they all will join. Okay? Because they know everything about each other. This is something called common knowledge. When two nodes know that what they know reciprocally, this is called common knowledge, and therefore this is a case where you can have a revolution. And the point is that there's enough connectivity so that everybody knows everything about the others. Okay? And this gives us kind of the clue, the thing to know about collective action. It means, so the summary is on the bottom. Huh? You need, first of all, a lot of strong ties, but if you have common knowledge, then you can do collective action. So the trick is getting common knowledge. Okay? So let me explain a little bit more in detail. So the nodes' decisions depend on them reasoning about what the other nodes know. It depends on the strong ties, etc. So this is kind of, hard to understand what's really going to happen. If they just want to pass information, the first wave, it's enough to have weak ties, loosely coupled communities, that's enough. But if you want to do an action, adopt it, go out on the street, if you want to do a collective action, it's not enough. You need strong ties. So the first thing is, you need if you have a tightly coupled community, you have many strong ties. So you need many strong ties. And if you have many strong ties, then the community can obtain common knowledge, where everybody knows what everybody else knows reciprocally. So an example of that is a secret rally. That means everybody is invited into the same room secretly, and they make a decision. And everybody sees the other person, and they say, we decide tomorrow at 3 o'clock, we're going on the street. So every person knows that the other person knows that, and the other person knows that they know that, and the other person knows that they know that, and so on, because they're all in the same room looking at each other. Okay? And so a secret rally is an occasion where the community can obtain common knowledge, where everybody knows what everybody else knows reciprocally. And that can lead then to the collective action. So to do a collective action, a sufficient condition for collective action is common knowledge. It's common knowledge. With common knowledge, you can decide on collective action. Okay? So that is for common knowledge. Let me explain now a little bit more socially. So now we're really getting into sociology, yeah? Common knowledge, where everybody knows. For example, in this room, if I say something, then each of you knows that I said it to that knows that the other person heard it too. So that becomes common knowledge, okay? That person A knows that B knows it, and B knows that A knows that B knows it, and so on. So that the knowledge is common between everyone, okay? And in an open society, that's very important. For example, a publicized speech or an article in a high circulation newspaper, it's not just the speech. It's not just the article. There's another message. They make the listeners aware that many others have also gotten the message. So if there's 1 million people reading the newspaper and I read that article, I know that 1 million people have read that article, and they know, all the subscribers, that I have read that article, okay? That is a form of common knowledge. This is what you get from freedom of the press. You get this notion of common knowledge. This is completely the opposite of limiting communication in a repressive regime. Huh? And there's many organizations giving common knowledge. It's not just secret rallies or newspapers. Many, many social institutions give common knowledge. This is an American example. America has this thing called the Super Bowl, where every year there's this huge football game between the two major football leagues. The champions play. All of the Americans watch this, okay? And there was a very famous commercial. So they made commercials during the halftime break. And there was a very famous commercial by Apple, Macintosh commercial. And since this was 1984, this was using Orwell example. And it said something like, why 1984 will not be like 1984. And you saw this woman runner with a big hammer running to the screen and breaking up a big screen of Big Brother or something, okay? So all the Americans saw that. And so this became common knowledge. So it becomes part of the culture. Everybody knows that everybody knows it, okay? And it's just a football game. And so many things. In Europe, it could be the Eurovision Song Festival, okay? Is somehow common knowledge. But also the football championships, okay? And so on, become common knowledge. Because it's like part of the culture. And here's another more political example. So this was in 2003, the American invasion of Iraq. Okay. Now in Islam, there's two kind of variations, two kind of different flavors of it. I won't go into it. Sunni and Shiite. It turns out the Shiite organization has a major advantage because they have sermons on the Friday in the mosques, and these sermons give common knowledge. All the people, the faithful attending that sermon, would know that everybody else knows something. So this means that there was information dissemination was much, much better in the Shiite community than in the Sunni community. Okay? So this is a typical example. It doesn't have to be political, it can be a religious gathering, anything. It all gives common knowledge. So common knowledge is very important, and if you want to fight against repressive regimes, common knowledge is very important, okay? And so this example kind of shows the importance, the three examples of the common knowledge, why common knowledge is an important thing, okay? And if you don't have it, you will have pluralistic ignorance, and you will make it easy to have repressive government, okay? So you can see we now go from internet into a little bit into politics. Okay, let me first give now summarize what we saw on cascading, but then I want to give a little bit of a summary of the whole course. And I want to give you some hints also for the exam. So first, for cascading, let me summarize everything in one slide. If you want to adopt innovations, it depends on your neighbors. And it's two waves: information, diffusion, and then the adoption. So it's two waves. We made a first model of cascades and clusters with a theorem. Okay? We defined a cluster. Each node has at least a fraction p of neighbors in the set, which is a cluster. And if you have a threshold, that's the decision of each node whether to flip, to adopt or not. And a complete cascade, which makes all nodes flip, will only occur if the remaining network does not have a cluster of density greater than 1 minus q. Because if that happens, then that cluster will not flip. Okay? We saw that. We also saw collective action. We gave an idealized model, showed the importance of common knowledge. So I explained pluralistic ignorance. When this happens when there's no information diffusion. So this is the importance of information diffusion. Communication is suppressed. Even a few weak ties are enough, but they suppress even those few weak ties. Okay? And if you want to make a collective action, so a group of people adopting something in a repressive society, you need many strong ties, and a sufficient condition is to achieve common knowledge. If you achieve common knowledge, then you can do collective actions. Okay? So that is the basic what we saw today. Okay. So now we're getting close to the end. Let me now give a kind of summary of the course. Since in this course, we saw lots of different things. We connected many different things. Networks and people, how they connect each other. And it's based on this book called Networks, Crowds, and Markets. So I strongly recommend that you use this book, because I'm following it very closely. And we take many disciplines: graph theory, game theory, sociology, also from economics, information networks, web structure, search, network dynamics, so the cascades, clusters, the power laws. And we define formal models, so many formal models. So I will give you a chart of that. Each of those formal models is somewhat simplified, so we can analyze it and compare it to the real world, but still it gives you a good intuition and you can adapt it for the real world. Okay? So, what happens now? So this course is supposed to prepare you from living in the world with the internet. So the society and the internet are influencing each other very strong, and we are now in a very fast track part of this, since now we have lots of problems with false information. So I haven't talked so much about that, false information, and also how do governments work with this information and so on. And so there's no real general law except that everybody is converging, okay? But let me first show you this diagram. So I made this diagram here, which is trying to summarize all of the models that we saw. And the basic notion is that everything is dynamic. It's always moving, and it's always trying to converge. And I start here on the left. So in social networks, we have people, and if they're friends or not. Remember, we have this notion of triadic closure. Friends of friends become friends. So these networks are converging to more and more dense networks. If you have enemies, then you have structural balance. So the networks are converging, so that you have stable groups of mutual friends or enemies. Okay, and then we looked at game theory. Locally, they're converging to Nash equilibria, where each player has the best response to the other. But society is not converging towards that. There's this tension. So governments are trying to achieve other kinds of optimality, Pareto or social optimality, and this is kind of modeling the tension between free market and government regulation. So you kind of need a balance between the two. And then we looked at auctions. A group of players are competing. The most important one is the second price auction. Ascending bid, which I like to call the James Bond auctions, which you always see in so many James Bond movies, are actually second price auctions. eBay is also a second price auction. And if you look at the way that Google prices links on the search engine, that is also a generalized second price auction. And the most important auction is second price because the dominant strategy is bidding your true value. So that really makes things very simple. That enormously simplifies the whole thing. And so this is the main trend for auctions. Okay, in markets now, instead of having a bunch of players competing, you actually have buyers and sellers. And they're kind of competing for buying the things. And the prices are a mechanism for conflict resolution. So the prices will fluctuate to find some kind of equilibrium. So this equilibrium can be called supply equals demand. You can also call it market clearing, where every buyer finds a seller. And we saw a discrete model of this with bipartite graphs. And we show how this thing is converging. And it's also a form of auction again. We show that this is also a form of second price auction. And both of these things, of course, we explain in terms of game theory. So everything is connected up. And then we added intermediate nodes, traders. And traders add two notions of monopoly and competition. And then there's a principle, if you increase the number of traders, you will increase the overall benefit to society, but you will reduce the individual trader profits. So the traders, they want to be by themselves, but the society wants more traders. Like supermarkets would be traders, for example. So we saw that, we analyzed that. Then we analyzed bargaining. When nodes are directly connected, like when you're buying a house. I'm looking at several houses, but other people are looking at houses too. So this gives a small network. And the power of a node depends on its position. And again, this whole thing is converging. So you have stability. So stability means nobody can sabotage the agreement. You have balance, that everything is considered fair by everyone, Nash bargaining solutions. And of course, humans don't like extremes. So that rules the bargaining. Then we talked about wedge search. Now we're looking at big networks again. So we had a lot of, I'm not actually putting, I should extend this a little bit. We saw many variations of this. This is converging to an equilibrium situation where you have kind of a fluid flow on the web graph. So new web pages arrive, it changes things. It's also linked around the walk, and we saw that. And we saw things like link farms, which I should put here also. which is how to cheat on the PageRank. And then we talked about cascades. This is when information kind of propagates. And there's two kinds. Information cascades, when decisions are made sequentially, one after the other. So people look at the previous decisions, and they kind of are organized according to that. And so this kind of tends to lock in early decisions, but it can be broken. So these things are actually not so good, and you want to break them. Then you have direct benefit cascades, where you have benefit when lots of people are making the same decision. We made a model of this, a continuous model. So this is a very different economic model than this one, which is discrete, even though they're both modeling similar system. We showed that you can have both stable and unstable equilibria. The unstable is like a tipping point, where you go from low, zero equilibrium to very high. So the trick for a company is getting above that tipping point. Sometimes you can turn the tipping point into a passageway if you do the right thing. And then today we talked about clusters. So we added the network structure to this. So that somehow tightly knit communities can block this kind of cascade clusters. And then there's techniques for getting over that. And the final thing is power laws and the long tail. Everything in social organically is organized according to power laws. And again, it's coming from some kind of an equilibrium when people tend to copy early decisions, okay? And this gives you power law behavior. So this is a lot of different things, but I really want you to try, when you study it, to see that there's some kind of a uniform principle underneath. So the principle is listed up in blue. Real-world networks are always converging to some changing equilibrium. And this is a general idea, and for each one of these points, we made a model, okay? So let me make a few comments on the exam now. So for the exam, you have to understand all of these models, okay? Sorry, but that's what you have to do, that's important. So I can ask you to explain any one of them. I can also maybe give small examples, okay? And there can be, it's a little bit more theoretical than other courses, but I can ask exercises that are related to the exercises you saw in the labs. So I can ask you to, for example, analyze games, give me Nash equilibria, and so on, or analyze certain kinds of networks, trading networks, or balance, or whatever. I can maybe ask you to analyze according to some of the models we have, or analyze, are there clusters in this network, or whatever. But not too complicated. The exam will be a set of smallish questions, okay, where the answer, it's all open, so no multiple choice. You will have open answers where you can draw figures and explain. And I will read all of your answers, okay? And the exam is on 15 points. 5 points corresponds to the midterm. I'm now finally grading it, okay? So you will get it before the end of the blocus. So I'm sorry about that, but it should have been much earlier. But you will get the result before the end of the blocus, guaranteed. And then there's the project, which also counts for 5 points on the final exam. And that one you will get very soon, in a few days. Normally you will already get points for that. Okay, so now we are at the end of this course. So I hope you liked it and you learned something about the internet. And I just want to wish you a good blocus now.